Okay, hello everyone. It's my great pleasure to share our work at ISMAR. And the title of our work is Digibird-based user experience analysis and time perception modeling in wire transformer in VR. In this work, we focus on how to model time perception and how it relates to user experience in virtual reality. And here is the outline of my presentation. And first, let's start with the word Digibird. Actually, Zigbers is a German term that literally means time givers. It refers to external cues that can influence our subjective time perception, for example, like the light or sound or other things. And in virtual environments, these cues can also include some artificially simulated factors. And since we are talking about time, there are some common experience we can relate it to. For example, when we are having fun or we are playing an engaging game, we will find that the time passes very quickly. And before we know it, the entire afternoon has gone. And in our daily life, we even have a saying that time flies when you are having fun. And similarly, in the classical flow theory, a distorted sense of time is considered one of the key indicators of entering a flow state. So together, this observation suggests that our perception of time may be closely linked to the user experience. And the existing studies have mainly focused on how different VR Zigbirds influence users' time perception, but few have explored the relationship between time perception and the user experience. We believe this gap exists because of the limitations in traditional research approaches. Previous studies often compare subjective time perception with physical time, but in reality, people are not very good at estimating physical time accurately, and more importantly, accurate time estimation doesn't reflect their experience quality. So based on this consideration, we formulate 3 research questions. Research question 1, how do different Zigbirds affect participants' time perception in VR? And RQ2, is there a correlation between VR time perception and user experience? And to better understand the mechanisms of VR time perception, we also propose the RQ3, whether time perception can be modeled by a deep learning method based on multimodal physiological data in VR. And so to address the RQ1, we built an experimental scenes with different Zigbirds, including VR task, light color, and music tempo. To address RQ2, we collected the participants' user experience data during the experiment. And to address RQ3, we also collected the participants' multimodal physiological data, including EEG data and heart rate signals. In summary, our main contributions are as follows. First, we built an VR experimental system to study how tasks like color and music tempo influence time perception. Second, since traditional approaches cannot effectively capture the relationship between physical time estimation and the user experience, we propose the relative subject time change method, or to say the RSTC method. These methods use a baseline condition to compare how time perception and the user experience changes across different experimental settings. And third, we develop a TPM-NIGHT, a deep learning model that uses multimodal physiological data to predict time perception in VR. This approach further can enable us to infer user experience change from physiological signals. So we have a research framework and how we choose these Zigbirds. First, let's look at the VR task factor. We refer to the attentional gate model. In our experiment, we adopted a spatial rotation task, a classical cognitive load paradigm, where participants are asked to select 2 correct shapes out of 4 options based on a target shape displayed on the virtual task board. And next, for the visual factor, we refer to the pacemaker accumulator model, which explains how arousal and emotional states can shape subjective time estimation. And in our design, we use the virtual environment lighting, the red and blue, as our visual variables. And finally, for the auditory factor, we refer to the entrainment theory and choose music tempo as the auditory variable. We also collaborated with the professional musicians to compose music pieces with different tempos for the experiment. Now let's listen to a short example. And this is a fast tempo. Oh. This no.
The joys of technology. Y'all can hear it? Okay.
Okay, let's continue. And this is fast tempo music. And this is the slow tempo. Okay, as you can hear, there is clear difference in the music tempo between these two pieces. And after selecting the experimental variables, we then designed the experimental groups. Actually, before the formal study, we conducted a 4-factor pilot experiment. We found that the VR task factors had a domain influence on time perception, which overshadows the potential effects of visual and audio cues. Therefore, in the main experiments, we separate the task condition and combine it in individual with other factors, as shown in the table 2. And the figure shows the device we use and the VR scenes corresponding to each experimental scenarios. And for each trial, we adopted a prospective paradigm in which participants were informed in advance that they need to estimate a 30-second duration. This design allows for a more accurate and reliable measurement of participants' time perception. And the procedure of each trial is shown in the feature. And the participant will actually to trigger the start of the experiment. And when they feel the 30 seconds has passed, they press the controller button to end the trial. This design allowed us to collect more precise time perception data compared with the traditional verbal reports or the UI-based inputs. We collected 3 types of data in this study. In short, we gathered the time perception data, user experience data, and the physiological data. To model VR time perception using physiological data, we designed the TPM-NET. This model takes both multimodal physical signals and the virtual Zigbee embedding as the input. It then predicts the user's time perception state through 2 core modules, the time perception feature extractor and the time perception predictor. We categorize the prediction result into 3 classes: underestimation, acceptable accuracy and overestimation. Noting that accurately estimation physical time is very challenging, so we use the acceptable accuracy. If you are interested in the model details, you can check our paper. And now let's move on the experimental results. We obtained many interesting findings, and I will present some key results. First, regarding the research question 1, how do different neighbors affect participants' time perception in VR? In this part, we compared the with and without groups regardless other conditions, and we also examine how visual and auditory neighbors interact with the task factor. The key findings can be summarized as follows. First, regarding the task factor, most participants tend to underestimate time, and this effect was especially pronounced in the group with a VR task. There was also there was no significant difference in relative time estimation between with and without task groups, suggesting that maybe the ISTC method can effectively eliminate the variable caused by different experimental factors, as well as individual differences such as age and gender. And second, regarding the light color factor, when comparing to the physical time, participants generally overestimate time, especially with tasks. Considering the relative time change, blue light causes time overestimation, while red light leads to underestimation, stronger with the tasks. VR color light effects were consistent with those in the real-world environments. And finally, regarding the music tempo factors, in groups with VR tasks, fast tempo music leads to stronger relative time overestimation. In non-task groups, participants generally underestimate the time when music was present, as music diverts attention in the sense without a task. And about the research question 2, is there a correlation between VR time perception and user experience? And first, about the ISTC method, as we can see in the table 4, the proposed ISTC methods achieved a higher explanatory power compared with the traditional analysis. And also from the heat map comparison, a similar correlation trends was observed, but with the ISTC method with stronger and clear relationships by our methods. And about the conclusion, overall relative user experience change showed a positive correlation with relative subjective time as perception, especially for presence and engagement. And in the color conditions, strong positive correlations appears in overall user experience, presence, engagement, and immersion. And in the music conditions, correlation with time perception were weaker, particularly with a task. And finally, regarding the research question 3, whether time perception can be modeled by a deep learning method based on multimodal physiological data in VR. As shown in table 5, TPM9 achieved strong performance in predicting time perception from multimodal physiological data. And compared with commonly used physical baseline models, TPM9 showed significantly higher prediction accuracy, and these results demonstrate the potential of modeling VR time perception through multimodal physiological data. And now let's briefly discuss the limitations and the future work of this study. And first is about the participant sample size and the diversity. And second is the task-related factors showed a stronger influence than other factors. So future study could pay more attention to the task-related factor. And finally, this study mainly focused on time interval estimation, while another key concept, the passage of time judgment, was not included. although the relationship between these two dimensions is still under debate, but further work could integrate the path of time judgment for a more comprehensive analysis for the time perception in VR. And that's all. Thank you.
We have time for about one quick question while our second speaker gets set up. All right, well, we'll move on to our second speaker then.
Yes, thank you for the introduction. This paper was written by me and Anton Lammert, who was the first author of the paper, Laura Simon, Eva Hornecker, Jan Ehlers, and Bernd Fröhlich. A lot of research has shown that joint synchronized rhythmic activities can have pro-social effects, for example, dancing, drumming, or running. And they can increase, for example, partner likability, trust, group cohesion, or cooperation. So what if we want to make use of that in VR? In this video, you can see Anton and me performing a very simple form of rhythmic activity in VR, and I was trying to follow Anton's hand movements. For me, it seemed like I was moving in synchrony, but if we look at how Anton perceived our interaction, you see that for him, it seemed like I was moving out of sync. And this is due to network latency, and of course, this then might disturb those pro-social effects that I was talking about. If we think of a music or a dancing game to promote pro-social effects, we would have audio-visual latency, and in that case, there are two versions, audio lagging behind video or vice versa. In the case of video leading latency, also called positive asynchrony, we could, for example, have a conductor here in Seoul and an orchestra in Berlin. And the hand signal of the conductor takes time to reach the orchestra, and then the audio signal takes time to be transmitted back to Seoul. That's why for us as a local audience in Seoul, the music would seem to be delayed relative to the conductor's hand movements. In the case of audio leading latency, we could, for example, have an orchestra in Seoul and a dancer in Berlin dances in rhythm with the music. In that case, the audio takes time to be transmitted to Berlin, and the signal from Berlin takes time to be transmitted back to Seoul. So for us in Seoul, the dancer would move delayed. But since we can only reduce latency to a certain degree, the relevant question for us would be, what factors influence the perception of latency? Our earlier work has shown that frequency for sure has an effect, but what we don't know yet is whether also rhythmic interaction plays a role. So whether it hides latency or makes it more noticeable. And we also wondered whether maybe physiological factors could maybe indicate in real time whether users still feel in sync, so similar to the paper that was presented before me. And our earlier work suggests that latencies cause greater pupil dilation because of the additional cognitive effort that is needed to integrate misaligned stimuli. However, this was, in this previous experiment, only shown in a desktop environment, and we now want to test whether it holds in interactive VR. These research gaps lead us to the following questions. First, does rhythmic interaction influence synchrony perception of rhythmic stimuli? And can pupil dilation predict the synchrony judgment of rhythmic stimuli in VR? And for this, we created a 2x2 factorial design, and we varied the stimulus frequency, namely 0.5 or 1 Hertz, and we varied whether participants only observed avatar's hand movements or whether they themselves waved along, so whether they interacted. You can see that here, in that case, the participant was interacting. We simulated latency in this experiment by varying the so-called synchrony onset asynchrony inside each of these cells, and with values between 0 and 400 milliseconds, and the sign here indicates whether it's audio or video leading latency. In each trial, we started with a 4-second baseline phase without sound, so participants could entrain to the avatar's hand movements, and during this phase, we also measured the pupil dilation baseline. After those 4 seconds, a sound was played each time the hand was at its maximum position, so either here or here, and here we varied the asynchrony. Each trial lasted at least 8 seconds, and after participants had entered their binary synchrony judgments, the trial ended. The setup looked like this. We used the HCI Vive XR Elite with a Vive full face tracker, and we chose a seated setup to reduce the physical fatigue. For this presentation, I will focus on our 2 main dependent variables, and we start with results related to our first research question: does rhythmic interaction influence synchrony perception of rhythmic stimuli? This diagram here shows the mean fraction that was rated as synchronous for each asynchrony. In blue, you can see conditions where participants waved along, and in red, conditions where participants only observed the avatar. The results of 32 participants showed that interaction, so waving along, had a significant influence on synchrony judgments, but only during audio leading asynchrony, so here on this left side. So why is that? When we look at this red line, so at conditions without waving, if you compare the right and the left side of the graph, you can see a slight asymmetry, right? And that is because auditory signals are processed faster than visual ones. This is a very typical finding for synchrony judgment tasks. When we add interaction, however, we assume that this additional task reduces sensitivity to small timing mismatches, and maybe also because motor engagement can help to bridge the gap between 2 misaligned stimuli. As a result, early sounds are more easily accepted as synchronous, but for video leading, this effect could not be found, because here we are already more tolerant, so interaction does not add much change there. So we can conclude that rhythmic interaction, in this case waving along, increases the tolerance for audio leading temporal offsets. To quantify this change in synchrony judgments, we employed the so-called at-a-glance model. You can think of this as a more detailed way to look at synchrony judgments. And we used this model to fit functions through the judgment data points. And 3 key parameters of these fitted functions are the window of subjective synchrony. This describes the range of asynchronies within which participants still perceive synchrony. And we have the left and the right decision criterion, which marks the threshold where participants kind of switch from judging something as synchronous to asynchronous or vice versa, mathematically the point of the steepest change in the fitted synchrony curve. If we now investigate the left decision criterion, we can again see that rhythmic interaction had an influence, shifting the left decision criterion by up to 55 milliseconds. To make this more concrete, here's an example of the function from participant 9. In the no interaction condition, the left decision criterion was at around minus 30 milliseconds, but under interaction, you can see that it shifts further left to about minus 90 milliseconds. For the right decision criterion, which would be somewhere here, this effect, however, could not be shown, which is kind of in line with what we saw earlier in this first diagram, where the effect was also only visible on the left side. Looking at the window of subjective synchrony, we can see that interaction broadens it up by up to 45 milliseconds. And looking at participant 9 as an example again, you can here see the window of subjective synchrony for a no interaction condition, and that it broadens in interaction conditions. For our second research question, so whether pupil dilation can predict synchrony judgments, in VR we analyzed a quality control subset of 25 participants. And we found that pupil dilation was significantly influenced by the interaction. However, we found no strong link between pupil dilation and synchrony judgments that would make it a reliable predictor of perceived latency. Looking only at non-interaction trials and at a smaller offset, we can confirm the results that we found in our previous study in non-VR. The larger the asynchrony, the larger the pupil, so we have this nice curve here. And we interpreted this as reflecting cognitive load from trying to misaligned stimuli, trying to integrate them. But once the gap becomes too large, so at the sides, we propose that the brain stops linking them, stops perceiving them as one signal, and pupil size no longer increases. So to summarize, we found that rhythmic interaction increases tolerance toward audio-leading asynchronies by up to 66 milliseconds. This might be connected to previous findings that cognitive load modulates multisensory integration, and pupil dilation was significantly influenced by asynchronies, which might reflect cognitive load from integrating those misaligned stimuli. However, like I said, pupil responses did not consistently predict perceived synchrony, likely because that reflects an unconscious effort rather than really a deliberate judgment. However, there are still factors that may have influenced our results. For pupil dilation, future studies should control for changes in the scene luminance and maybe consider combining pupil measures with other physiological responses. The previous study, for example, used EEG. We could do that. Or with movement data, so we can really better isolate those perceptual effects. It would also be important to examine truly bidirectional settings. So here we only had an avatar, and in bidirectional settings we would have mutual entrainment, like for example in a VR dancing games where both partners really adapt to each other. And our results suggest that in such contexts, interaction itself makes those small temporal offsets that are inevitable in VR, makes it less noticeable, particularly when the audio leads like it would be typical in VR dance scenarios. And with that, thanks for your attention. We have made the code implementation and the anonymized data available to support further research. And if you have any question, please feel free to reach out here directly to me or also to the first author, Anton. Thank you.
We have a couple of minutes for questions. Does anybody have a question? Quiet group. Did y'all consider other modalities besides visual and audio? And do you have any thoughts about that?
Yeah, so for this experiment, we didn't, and we focused on audiovisual just because it's so typical for VR settings. And if we think about those pro-social effects that I mentioned earlier, the probably first thought that comes to mind is those dancing games or music games, and there we would have those audiovisual stimuli, and that's why we focused on that. But of course, we could also study other modalities, and related work has shown that the synchrony perception varies a lot, not only between participants, but also between modalities. So that's why we wanted to include those physiological measures, because that would give us a chance then to measure synchrony perception independent from any modalities or other influencing factors.
Thank you. All right, well, we can move on to our third speaker, unless there's any final questions. All right.
Hello, I'm Takahiro Ito from the University of Tokyo, and today I present our work titled Enhancing Dazing Sensation through Blink and After Image Presentation in Virtual Reality. In virtual reality, dazing sensation is a crucial element for enhancing immersion. This applies not only to entertainment, such as lighting effect in VR concert, but also to practical training applications like simulating the glare from the oncoming car's high beam and driving simulator. Therefore, the effective presentation of brightness is important for the experience in VR. Various studies have been addressed how to present dazing sensation in VR. One approach is the physical reproduction of high luminance light. Why this method achieved high luminance? It comes with a high cost and potential danger to the eyes. Another approach is the simulation of biological responses. This method is low cost, but it has not yet succeeded in achieving a convincing sensation of high luminance. So our study aimed to present a sense of dazzle safety and at a low cost without using high luminance light. Previous work has focused only the glare effect, which is biological responses that occurs at the moment of viewing dazzling light. Our research, in contrast, focuses on the after effects of being exposed to dazzling light, such as blink reflex and after image. So we propose a method for simulating after effects of exposure to a bright light, such as blink reflex and after images. This slide illustrates our concept. We combine the conventional visual effect for glare with our approach method. When a user is exposed to dazzling light in VR, our system introduces two sensations, soothe blink sensation and soothe after image. Soothe blink sensation is generated by combining eye-around vibration with a brief blackout of the screen. Soothe after image presents a lingering image that transitions in color and intensity depending on the user's gaze and physical blinks. To generate soothe blink sensation, we focused on the darkening of the virtual field caused by eyelid occlusion and focused on skin deformation. The darkening of vision is achieved with a simple blackout effect that the left side video. And based on the previous works, vibration stimuli can create the illusion of skin deformation. And it has also been suggested that low frequency vibrations around the eyelid can evoke the sensation of blinking. This left study induced the sensation of skin deformation through vibration and visual stimuli. And the right research attempts to present sensation of impact and blinking by applying low frequency vibration around the eyelids. So in our study, the feeling of skin deformation is stimulated using vibratory stimulation to the area around the eyelids. For implementation, we use a MetaQuest Pro headset to obtain users' gaze data. The linear resonant actuators were attached to HMD to present vibration to the upper and lower eyelids. The two upper linear actuators were mounted to provide vibration to the upper eyelid. and the two lower ones for the lower eyelid. And we conducted a preliminary user study. We determined the parameters for the vibration and blackout. About presenting vibration, to stimulate the natural movement of the eyelid, we introduced a specific time gap between the upper and lower vibration. The sequence begins with a vibration to the upper eyelid. Then 12.5 milliseconds later, we vibrate the lower eyelid. And finally, after 25 milliseconds after that, we apply a second vibration to the upper eyelid to complete the sensation. And for presenting blackout, we employed a method that blacked out the entire field of view at once. This blackout of entire visual field was synchronized to start at the exact same moment as the vibration sequence. Blackout lasted for a duration of 75 milliseconds, after which the user vision was returned to normal. And here is a specific vibration parameter we used. The vibration itself was a 30 Hz sine wave. And to control the intensity, the amplifier was set to 100%, and the PC's system volume was set to 20%. And for the third after image, based on the previous research on after image presentation for 2D displays, changes in after image color and intensity and gaze following are applied to each eye respectively. The figure on the left side is a simulation showing how the after image color changes over time, which is represented by the horizon axis. In this example, the color shift from a light green to a deeper shade as time progresses. And the short video on the right is an example of after image presentation. We made after image position track the user's gaze and introduced a periodic fluctuation to its intensity. And to further enhance reality, we introduced a complementary after image. When we blink, after image we perceive is known to be close to complementary color. As shown in a diagram, when we use a blink while an after image is displayed, we change the color of the after image to its complementary color. We newly incorporate complementary after image and interactively change the after image color based on the user's physical blinking. To validate our method, we conducted an experiment. The object was to evaluate how pseudo blinking and after image presentation affect the user's dazzling sensation. Participants experienced the light stimuli under each condition and rated the dazzle sensation, preference, and realism. We used a 2x3 experimental design. The factors were pseudo blinking and pseudo after image. pseudo blinking factor without the blink effect and with blink effect. In without blink effect condition, we did not apply any vibration to the eyelids, nor did we black out the user's vision. In with blink condition, we presented both stimuli, the vibration to the eyelid, which had the time gap between upper and lower eyelid, and blackout of the visual field. And after image presentation, without after image, normal after image, complementary after image. Without after image condition, we simply did not present any after image. In the normal after image condition, we present a standard after image, but it did not change into its complementary color. In the complementary after image condition, we present an after image that changed to complementary after image when user blink. Here is the result. This graph shows the score for dazed sensation. In this graph, the colors represent the different after image condition. White is without after image, a green normal after image, and pink complementary after image. And the pattern of the curve indicates the blink effect. Hatched one is with blink effect. And the score was significantly higher the condition where the pseudo blink effect and the after image effect. This indicates the dazzling sensation was enhanced by presentation of the pseudo blinking and after image. And this graph shows the result of realism. The presentation of both pseudo blinking and after image resulted in higher score, higher realism score. So realism was also enhanced by presentation of pseudo blinking and the after image. This is a summary. Thank you.
Do we have any questions? I had just a quick question. On the setup of the head-mounted display, did the actuators actually touch the person, or did it just touch the, was it just vibrating the headset on the top or the bottom?
Thank you for your question. Actuator was just attached to headset,
Okay.
and also attached to
Both.
both users.
So it was between kind of where it would touch their skin, where the headset would touch them to kind of force it to be touching them? Or so it's between the headset and the skin touching both?
Touching both. Yeah.
Okay, great. All right, it doesn't look like anybody else is jumping up for questions, so let's thank our author.
Evaluating and predicting speed misperception. This is the first work to comprehensively explore the combined influence of key visual cues on the speed perception. Imagine we are immersed in a VR scene, sitting inside a fast-moving car. The vivid visuals makes us feel as if we are truly speeding forward. This example shows how visual information in VR can strongly influence our perception of motion and speed. However, since this sense of the speed is triggered by the visual cues, the visuals can sometimes mislead our perception. To help you better understand this phenomenon of the speed misperception, let's take a look at an example. Let's take a closer look at this driving scene, where the surroundings swiftly pass by us. And let's experience this with a different visual content. Here comes the question. Which one of the motions do you perceive as faster? Based on our user study, 90% of the participants found the first one to be faster. However, the truth is they are at the same speed. So we are wondering that what factors in the visual stimuli is causing our speed misperception in VR and AR. To comprehensively understand how humans misperceive speed in the visual content, we utilize the Gabor patches as our visual stimuli, because their greeting structure closely approximates the receptive fields of the neurons in our human visual cortex. In addition, we adjusted the contrast and the spatial frequency to investigate how these image features influence our speed perception. As an important factor in the foveal and peripheral vision, we also examine the effect of the eccentricity on the speed perception. Moreover, temporal frequency, which determines the velocity of the visual stimuli, plays a crucial role in this research. Overall, we investigate human speed perception across multiple dimensions, including contrast, spatial frequency, temporal frequency, and eccentricity. Our study followed the method of adjustment protocol, where participants adjusted the speed of the center Gabor to match the speed of the peripheral Gabor to the best of their perception. After they completed the task, we measured the ratio of the speed between the peripheral Gabor and the center Gabor. This allows us to calculate the ratio of the perceived speed to actual speed, revealing how users misperceive motion under the different visual conditions. We call it perceived speed ratio. Based on our data, we found that people tend to overestimate speed while viewing higher contrast stimuli. Moreover, this increase in perceived speeds becomes more pronounced as the spatial frequency increases. However, we observed that the perceived speed ratio decreased with the higher temporal frequency. And similar to the temporal frequency, the effect of the eccentricity on speed perception is significant. The eccentricity reduces perceived speed. Our study provides a systematic understanding of the visual-induced speed perception. Moving forward, we aim to evaluate these effects in more general and complex VR environments. While prior work has investigated the combined effects of the temporal frequency and eccentricity in the VR settings, the stronger effects of the spatial frequency and contrast on speed perception have remained underexplored. So we aim to address this by testing our findings in realistic scenarios. To differentiate with the pilot study and pursue a more generalizable situation, we designed a study in natural VR scenes. As shown, the user experienced a daily walking situation in this study. For the spatial frequency condition, because spatial frequency being an inherent property of the scene content, influenced by the object distribution, texture, and lighting, could not be directly and precisely controlled through post-processing filters. Therefore, we adjusted the spatial frequency by selectively retaining or removing the high-frequency objects from the field of view. And the users sequentially experience the scenes with different spatially frequencies. For the contrast condition, we implemented a camera filter to control the overall scene contrast. As illustrated, users also experience the scenes with the varied contrast. The evaluation study conducted a two-interval forced choice task, letting the user to differentiate the speed variance between baseline scene and the adjusted low spatial frequency or the low contrast scene. Our study spans 3 immersive scenarios in VR, including the walking, driving, and the gaming. The statistical significant results indicates that the participant consistently misperceived the speed as slower in lower frequency and lower contrast scenes. Our experiments confirms that visual content significantly influences perceived speed, demonstrating its generalizability to the immersive VR environments. This has encouraged us to develop a generalizable model to predict the perceived speed ratio, considering the various visual conditions, including contrast, spatial frequency, temporal frequency, and eccentricity. To model the multi-dimensional relationships while encouraging the local smoothness, we selected the radial basis function neural network. For the details of this neural network, please refer to our paper. Therefore, our model can predict the speed perception in different contrast, spatial frequency, temporal frequency, and eccentricities. The proposed model drives us to a couple of potential applications. Firstly, as a VR user, when viewing a dynamic scene, the visual vestibular conflicts may result as cybersickness and making us feeling dizzy. To address this issue, we could utilize our model and adjust the visual cues to decrease the perceived speed. This approach could potentially compensate the visual vestibular conflict. Other than using our model for post-hoc scene analysis, we could also use it for synthesis. Adjusting the perceived speed ratio as 1, we can inversely apply our model. And it will tell us in what size of the visual properties we can synthesize our scene to reduce the speed misperception. By knowing the size of the image features with minimum speed misperception, we can synthesize the scene with a certain size of the visual properties, and it could deliver the VR with corrected speed perception. We propose a perceptual guided framework for the speed perception prediction under various visual properties, and demonstrated 2 potential applications. We believe this work leaves many fascinating future directions to explore. For instance, By additional factors, we envision our model can be supplemented as a perceptual metric to enhance our understanding of the speed perception. In addition, a natural next step would be to extend our model into the human-in-the-loop application, such as evaluating the interactive task performance or enhancing navigation guidance. Thank you for attending my talk. I hope you enjoy it.